Turbo machines are mechanical devices with several blades connected to a rotor that adds or extracts energy from a fluid through dynamic interactions, mostly work transfer. These fluids can be gas, vapor, or liquid, all of which have the same operating principles, however with different fluid properties they have different fluid dynamics. These machines may contain a housing unit around the rotors for an internal passage formation, or may be unducted like a windmill. Turbo machines have three types of flow. Axial flow is where fluid maintains an axial direction from inlet to outlet. This is shown in figure B, where you can see fluid flow is parallel to the axis of the fan. Radial flow is when fluid comes in radially across the blades towards the center of the fan. And mixed flow has both axial and radial components from inlet to outlet. When looking at energy transfer within a turbo machine, we're going to consider a fan with angular velocity W and fan radius R. Here, blade speed is then represented by capital U, which equals WR. In this case, capital V will denote the fluid's absolute velocity, and W will be its relative velocity. Its absolute velocity is equal to its relative velocity plus its blade speed. Now looking at figure B, we see that the geometry of the fan blade pushes the fluid, causing it to change direction. This direction change is caused by a tangential force in the same direction as the blade motion, ultimately changing the value of capital V, which is its absolute velocity. Now, whenever the blades are the one moving the fluid or doing work on the fluid, the machine is considered a pump and costs energy to operate. When the blades are moved by the fluid, in other words, the fluid is doing work on the blades, the machine is a turbine, which then generates energy. The turbines and pumps spin opposite directions, assuming equal fluid flow and blade geometry. When considering momentum of a turbo machine, we think of work. Work can be calculated as force times distance, or torque times angular displacement. Here torque is denoted as capital T and angular displacement as lowercase w. Now if shaft torque, which is the force acting on the rotor to cause it to spin, and the rotor rotation are in the same direction, the turbo machine is a pump. And if not, and the two are in opposite directions, then the turbo machine is a turbine. For a turbo machine with steady state flow, we see that the sum of torques is equal to the moment of momentum, otherwise known as the angular momentum. Now, a 1D simplification of this equation gives us that the shaft torque is equal to M2 R2 V2 minus M1 R1 V1. Here, 1 denotes inlet, 2 denotes outlet, M is the mass flow rate, R is the radius, and V is the velocity in the angular direction. Now, as stated above, work equals torque times angular displacement. And so if we sub in the equation for shaft torque, we find that the shaft work is equal to U2 V2 minus U1 V1. Here, U is the blade speed, which we know equals angular displacement times radius, and V is again the velocity in the theta direction. Now, looking at these equations, they tell us that the most efficient pump will increase kinetic energy, flow radially outward, and decrease flow within blade passages. Now, these relations would be flipped for the most efficient turbines, where kinetic energy would be decreased, flow would be radially inward, and flow within the blades would accelerate.
In the next section, we talk about centrifugal pumps. They consist of two main components, which is a rotating impeller and a stationary casing. As the impeller rotates, it adds energy to the fluid, and as the fluid discharges into the casing, it converts its kinetic energy into pressure. A specific type of centrifugal pump is the diffuser pump. These are generally larger designs that use diffusion vanes to slow fluids down before they reach the casing. Centrifugal pumps come in many different variations. For example, with the impellers, they can come in an open or enclosed arrangement. The open one has blades exposed on one side while attached to a backing plate on the other. The enclosed or shrouded impellers have the blades covered on both sides. In addition to this, the impellers can have more than one fluid entry point. The single suction impellers have fluid entering on only one side, while the double suction impellers have fluid entering on both sides. There's also different pump types. A single stage pump has only one impeller mounted, while multi-stage pumps have several mounted in series. Here we talk about pump parameters. Under efficiency, we have the operating point. This is determined by charting the system curve and the pump performance curve to find the intersection. You can see that here in the diagram to the right. Net positive suction head is the difference between total head and the liquid vapor pressure head. Underneath that, you can see the calculation for that. There are two types, actual and required. The NPSH actual is useful for determining how high above a fluid surface the pump can be placed before dropping below the NPSH required. The required threshold shows when cavitation can occur, which will then decrease efficiency and increase wear in the long term. Pump scaling laws are used to determine the rates of a pump under certain circumstances, which can then be applied to other pumps undergoing the same or similar conditions.
Section 12.6 discusses axial and mixed flow pumps. Axial flow pumps are pumps whose head is due mostly to the tangential force exerted by the rotor blades, and because of this, they're often called propeller pumps. They're most desirable for drainage and irrigation because of their high flow rates and low heads, and they operate at very high specific speeds in excess of 9,000. Mixed flow pumps are a combination of radial flow pumps and axial flow pumps, and they operate most efficiently between their two specific speeds, from about 4,000 to 9,000. Section 12.7 discusses fans. Fans are commonly used for both cooling through convection and for ventilation. They generally operate at low rotational speeds, but have the ability to move large volumes of gas relative to their size. Depending on their location in the system, fans can be called blowers, exhausters, or boosters. Blowers are located at the system entrance, exhausters are at the exit, and boosters are located somewhere within the system. Fans can be centrifugal, mixed, or axial flow. Because fans have a slow rotational speed, the gas density remains relatively constant and can therefore be assumed as incompressible when working with fan problems. Turbines are machines that are used to extract energy from flowing fluid, like a stream of water. There's two main types of turbines, impulse and reaction. Impulse turbines work similarly to water wheels, where a stream of water flows underneath and runs into buckets which cause the rotor to move, producing torque that is used to create energy in some way. A common example of this is called the Pelton wheel. It's seen in the top figure on the slide, and they usually have a high head and a low flow rate. Reaction turbines are similar to impulse turbines, however they're encased with the fluid that is performing the work. Turbines are seen in the bottom figure on the slide. These turbines can either be centrifugal, mixed, or axial flows turbines. Reaction turbines are much more efficient at higher speeds, and they have a low head and a high flow rate.